Thanks to all the organizers for putting together this wonderful conference, and thanks to Jason for the very nice talk that'll let me kind of speed through the first slide or two of my presentation. So I'm sort of continuing the theme. I want to talk about a very cool new result with Michele D'Addario, Mark Dukes, Sasha Irachi, Ivan Leborn, and Anna van den Wynyard, which relates these shuffle theorems that we just heard about to the sort of the combinatorial dynamical game of the abelian sandpile model. So to start, I'm going to recap the shuffle theorem of Carlson and Mellett. This is going to be the compositional form. So now we're extracting coefficients of a slightly more complicated symmetric function. That's what these angle brackets are. If you're not familiar, these are the Hall inner product on the ring of symmetric functions. And so the way I want to express it for this talk is the right-hand side is a sum over parking functions, which I'm going to view as a class of decorated dict paths. So this is going to be a dict path like we saw before with north and east steps staying above the main diagonal, but now we're going to put numbers on each of the vertical steps, and we're going to insist that the numbers are increasing as you read up each column. So in the previous talk, we heard about these two statistics, DIND and area. I'm going to use a different formulation, which comes from a bijection with the lower in Remmel. And this changes the roles of Q and T a little bit. And the first one, Q is to the DIND, T is to the area. Now, Q is to the area, and T is to some new statistic called PMAG. So what's PMAG? Well, as before, we define some word and we compute some permutation statistic on it. This one is defined recursively. It's a little more complicated, I would say, than DIN. So you start with some set C1, which is the labels in the first column. P1 is the maximum of C1. And then you define a CI and a PI recursively. This gives you a word P1 through Pn. And then PMAG is you reverse this word and take the major index. So this is, in the grand scheme of things, not terrible as statistics go. But it is something that's recursive, and so it's a little hard to wrap your head around, at least in my experience. So just to give you an example of like what these kinds of computations can look like, here is a parking function. This is in PF 43, 32. And so as we see, it's a dict path. It's got labels that are ascending up each column, and we can compute the area just by reading the number of cells, full squares in between the dict path and the diagonal. And then the parking word is down here. I'm going to claim that that's the parking word, and if you reverse it and get the major index, you get 6. And the total area is 35. Okay. So that's sort of the classical setup. So now I want to change gears rather suddenly and talk about the abelian sandpile. So throughout, there's lots, calling it the abelian sandpile model is a little misleading. There's a bunch of different versions of it that have various utility for different kinds of problems. The version we're going to talk about is on finite graphs with a sink. So we'll let G be a finite graph on vertex set 1 through n, and it'll have a sink 0. And a sandpile configuration is just going to be a map from the non-sink vertices to the non-negative integers. So you can just think of this as giving kappa of v many grains of sand to each vertex. So over here, we've got a graph G. You might notice that the colors are a little similar to the ones that were used on a previous slide. That's totally a coincidence. And if we, for any vertex V, if kappa V is at least as big as the degree, we say that V is unstable. And an unstable vertex can topple and donate a grain of sand to each of its neighbors. And just for convenience, the sink can always topple. You can kind of think of it as a central bank, if you like the poker chip version of it, of the chip firing game. And so the sand pile model studies the dynamics of these kinds of configurations as you let stuff topple and how it might relax down to some kind of static state. Sorry, and we say a configuration is stable overall if no vertex is unstable, except for the sink. So among the stable configurations, there's a class that are interesting called the recurrent configurations. And there's several different definitions of this. The one that we're going to use for this talk is the following. So we say that kappa is recurrent if after you topple the sink to make it unstable, there's some order V1 through Vn of the non-sink vertices so that V1 is unstable and Vi is unstable after toppling Vi minus 1. And you can check that once you've toppled all n non-sink vertices, you'll get back to your original configuration. And it's another kind of fun fact that's useful technically, and if you're as into posets as I am. Recurrent configurations are an order filter under pointwise less than or equal. So if you've got two recurrent configurations, or if you've got if you've got a recurrent configuration and you've got something that's bigger than it but is still stable pointwise, so at every vertex, then the bigger one is also recurrent. And an upshot of this is in the special case when G is just Kn, we're assuming the sink is not counted in this n. Kappa is recurrent if and only if some rearrangement is above the staircase n minus 1, n minus 2, 1 down to 0, which, if you're familiar with the sort of more classical definition of parking functions, ought to give you some idea that there's some kind of connection. Right? This is a very parking function kind of condition. Okay, so now we get to some new stuff. In our paper, we define a class of graphs that we call clique independent. So we let mu and nu be integer compositions with mu plus the sizes adding up to n. And we define a graph G mu nu on vertex at 1 through n. So each part of mu gives you a clique of size mu I. And each part of nu gives you an anti-clique or independent set of size nu I. And then, so for example, here we've got a clique of size 4, a clique of size 3, an independent set of size 2, and an independent set of size 3. So the cliques are in black and olive, and the independent sets are in blue and red. And then we want all possible vertices among all possible edges among vertices that are in different blocks. So there's no edges within the red vertices, but there's an edge from each red vertex to every other vertex, and so on. And then we're going to choose a particular ordering of the vertices just for convenience. And then we'll define G hat to be G mu nu along with this dominating sink vertex. So the sink is connected to everybody. And this running example that we've been looking at is G hat of 4, 3, comma 2, 3. So here we're allowing compositions, not just partitions. So we don't necessarily need the parts to be strictly to be decreasing in length, although of course rearranging them is going to change things, but only in a controlled way. And again, any similarities to this parking function that I drew a few slides ago is totally coincidental. Absolutely no reason that I would do the same thing. And so now we can go back to sandpile configurations on these graphs. Uh, these G hat mu nu, any sandpile configuration is going to admit an action of the Young subgroup S mu cross S nu, by which I mean we're allowed to freely permute the number of grains within each of these blocks, right? From the point of view of the graph, I can't really tell other than the label. So what I'm going to do is I'm going to pick a particular representative of each orbit so that within these sort of clique blocks, if I is less than j, then kappa of I is greater than or equal to kappa of j. And in the independent blocks, if I is less than j, then kappa of I is less than kappa of j. So for example, this configuration over here is both sorted and recurrent. As you can see, within the black clique here, the number of grains is weakly decreasing, same as in the olive clique. And then in the red and the blue independent sets, the number of grains is increasing. And then between cliques, between these blocks, we have no conditions about the number of grains. And so this brings us to our main result, which says that we can actually compute these coefficients of nabla En in terms of these sorted and recurrent configurations. And so first of all, this is pretty cool because I was way more familiar with sandpiles than I was with parking functions when I started this project. And so this is something that I think for a lot of people on the more dynamical side of algebraic combinatorics is something that they can get their heads around a lot easier. But also the statistics are significantly simpler. And so they're much more tractable to get your hands on. Okay, area is pretty easy, as is this statistic level. So we have q to the level, t to the delay. Level is the total number of grains minus the total number of non-sync edges. And this had popped up in a few different places as being related to area. But the new statistic and the thing that gives us this QT statistic is this thing called delay. And this is computed by a very simple algorithm. How do you compute delay? You topple the sync, and then as long as some vertex hasn't toppled, we traverse the vertices in decreasing order. And whenever I get to something that hasn't toppled, if I can topple it, I do. And if I don't, delay goes up by 1. And that's it. So this is a very local kind of condition as opposed to PMAG, which is kind of global. You have to always be paying attention to everything going on. This is a very kind of local condition. So here's an example, and I'm going to claim that the level is 35 and the delay is 6. But rather than take my word for it, Anna made a very nice animation computing this, which I want to end my talk with. So while this is going on, I just want to thank everybody for their attention. And also, I still think it's really cool.
Thank you very much, Alexander.